Now we've just seen that a proton and a neutron, when they're on their own, when they're not stuck to anything, they have these masses. But when they are stuck together in a nucleus, their mass is less. Now, we haven't made a mistake here. Mass does actually disappear when nuclei form. So you've heard me right, mass disappears. Now, in chemistry, you'll have learned that mass is conserved in chemical reactions, and that's true, but these are not chemical reactions, these are nuclear reactions, and mass is not conserved in nuclear reactions. Okay, so let's take helium as an example. We're going to make a helium nucleus from 2 protons and 2 neutrons. So the total mass before there is the mass of 2 protons plus 2 neutrons. That's the total mass, and you can see our new atomic mass unit working out nicely there. But the mass of the helium nucleus is only this, and so that means that 0.029 U of mass has gone missing when this nucleus formed. And we have a name for the mass that goes missing. It's called the mass defect. So this is the mass that is lost when constituent protons and neutrons stick together to form a nucleus. But what happens to that mass? Well, we already know the answer to this because it gets turned into energy and then radiated. Einstein's most famous formula will tell us for this much mass, put it in there, and this will tell us how much energy that mass gets turned into, and then that is the energy that is radiated when the nucleus forms. Okay, so we're going to do the calculation. We do need the mass in kilograms, so we need to convert into kilograms first of all. There we go, and then that is the mass that we're going to put into the formula, and it comes out as this, rounding to 2 sig fig at the end. Now you will find a slightly different value online because I've used rounded numbers up here a little bit. Okay, so remembering that this was the nucleus forming, so mass was lost, so energy was released. Now we're going to think about going the other way. What if I had a helium nucleus and I wanted to pull it apart into its constituent nucleons again? Well, I'd have to supply that energy because I need to make the missing mass back again. So if I want to pull the nucleus apart into its constituent nucleons, this is how much energy I'm going to need to supply because it needs to get turned back into mass to make the separate protons and neutrons. This concept is called the binding energy. It's the energy required to pull the nucleus apart into its constituent nucleons. Now you can see it's a very small number of joules, and so you're going to see lots and lots of binding energies that are in electron volts instead, because again it just makes the numbers a bit easier to handle. So here's a nice juicy exam question worth 4 marks. And the information that you need from the data and formula booklet are the rest masses there. Okay, so we've got a beryllium nucleus there, and the first thing we need to work out is how much mass it lost when it was formed. So it's made of 4 protons and 4 neutrons, so add all those masses together and we get that. Now we're told the mass of the nucleus, and we can see that is a little bit smaller, so that's good, checking our work there. So when the beryllium nucleus formed, that is the mass of the constituents, that's the mass of the nucleus. I've got my 10 to the minus 26 there, and so this is how much mass was lost in kilograms there. Now we're ready to use Einstein's formula, so we put it in, there's that, it's called the mass defect, remember, mass defect in there, and we get this much energy. So this is how much energy was released when the nucleus formed. We've got 3 marks now, but we're not quite finished because what it asked for was the binding energy per nucleon. So remember that so this is the energy that was given out when the nucleus formed, so it's also the energy required to pull the nucleus apart into its separate constituents again, and so this is the binding energy. But binding energy per nucleon, well, how many nucleons have we got? We've got 8, and so the binding energy per nucleon is that for the 4th mark.